So we have three themes in this the first part of the workshop. The first theme is the different evolutionary transitions in individuality. So we had an overview presented by Rainey. Now we have the next chapter, okay, before the next coffee break, would be talks that are devoted, each one of them, to a separate transition, characteristic of the transition to multicellularity, and characteristics of the transition to coloniality. And the first talk is by Professor Rainey, who is now the director of the Department of Microbial Population Biology, Microbial Population Biology, and in Max Planck Institute, previously, originally perhaps from New Zealand, in the time. Can't see why anyone would like to leave New Zealand, but just been there last year. And if I have to choose a place to go back again, I choose New Zealand. Even though I've been to Germany too, still anyway. And so without any further comments,
So pleasure to be here. Thank you for the invitation. I'm already enjoying it, and I'm looking forward to interacting with so many people I don't know. I'm an experimentalist. I'm an evolutionary biologist. My nature and the kinds of questions we ask are mechanistic. I want to know both why mechanistically something happened, and I want to know how it happened. That's particularly important if you're thinking about establishing experiments to explore, for example, evolutionary transitions in individuality. I am going to speak to some extent on the transition from cells to multicellular life, but I want to do so first of all by placing this in a broader context. Something that we've been trying to do over the years is to work from our experiments to see what our experiments on the transition from cells to multicellularity might also have a more general nature. And I think we have got some very simple general formulation, mechanistic of transitions. So I'll present that first. I'm interested to try these ideas out on you. And I will just briefly touch on your experiments. So, evolutionary transitions in individuality. To be very clear what I mean by individuality, I am, and many others are, thinking about individuality of a Darwinian kind. I'm thinking about what participates in the process of evolution by natural selection. So here we have John Lennon, here of this Matryoshka doll series, and he is an individual, he's a Darwinian individual by being a member of a Darwinian population where he varies from other types, where these entities reproduce, and the offspring resemble the parental. Evolution 101. Any set of entities that manifest these properties participates in the process of evolution by natural selection. I still find that quite amazing to think of. This is all you need. Any set of entities that manifest these properties participates in this process of evolution by natural selection. No guiding hand necessary, no intentionality associated with it. And of course, the important thing to appreciate, again, it's easy to take this for granted, that the outcome of those entities that participate in the process of evolution by natural selection is adaptation at the level at which natural selection works. Individuality, as you are all well aware, and it's a pleasure to meet Erson, of course, as one of his book, with John Maynard Smith, pointed out, going back to Leo Bass, who had some sense of individuality, that at least it manifests at multiple levels. Here, if we take John as a multicellular organism, we delve down inside him, we find, if we go through his tissues and organs, that they're comprised of cells. Delve down inside of the cell, we find organelles, into the chromosome, into the nucleus, chromosomes, genes, and potentially we could go on further. Each of these different hierarchical levels, of course, reflecting a level where individuality manifests to some extent or other. There's basically a replicative process. There is the possibility of selection working at these different levels, often with conflict of interests. A sense, too, that life's hierarchical structure has emerged as a consequence of rare events in which lower-level replicating entities have become subsumed within higher-level self-replicating structures. So cells, the multicellular organisms. Of course, we can go beyond that in various ways, but an obvious way, to feature the next talk, is if we replace a multicellular human here with an ant or social insect of some kind, then we can think about colonies as units of selection, colonies that manifest variance fitness. So, why emphasize again? Because selection sees each of these different levels, each manifests some replicative capacity, and each participates in the process of evolution by natural selection. Conflicts I won't go into, but I'm sure you are aware of them. Switching here to think for a moment very specifically about the transition to multicellularity. In my mind, I think about it in terms of individual cells, particle cells here, that are multiplying. An initial stage, often thought of as the formation of simple groups. For any set of entities to live in close proximity to one another, there is necessarily a cost associated with competition for resources, swimming in the excrement of others. That invariably means that there needs to be some benefit to the group, the collective, for it to be sustainable. That sets the scene for the inevitable rising of defecting types here, asocial types. And many have considered these a seminal problem, of course, in the evolution of multicellular life. No sooner do we observe the evolution of a simple group, then we see the evolution of defecting types that will bring about the collapse of that group and the classic tragedy of the common scenario. The next stage I think about and label the evolution of individuality. This is the evolution of those Darwinian properties that enables an emergent nascent group to begin to participate fully in the process of evolution by natural selection. And just to spell this out, the entities that we start with, particles here, there's a Darwinian, there are inheritable variance in fitness at the level of the particles. And once we get to this stage here, there is heritable variance at the level of collectives, with the particles and cells nested within those collectives. Once we have this, we have a Darwinian machine, if you like. The form of multicellular complexity that emerges is variable, but that some form of multicellular complexity will arise is a given. We have a Darwinian machine at this stage. So to me, the problems in explaining transitions and individuality are precisely this. It's explaining the evolution of these Darwinian properties. So the evolutionary transition to multicellularity, and I would say for many of the other major evolutionary transitions, is synonymous with the evolution of these Darwinian. We're thinking about the evolution of entities that can participate in the process of evolution by natural selection at a so-called higher level. It's very often taken for granted that these properties, these Darwinian properties, exist, that they somehow come from nothing, that the properties that exist in the individual cells simply transfer up a level. But I think that's quite wrong. as others have pointed out, Lisa Mayer in particular, some time ago. If we think about reproduction in multicellular organisms, it's clearly a complex, it's clearly a derived trait. Heredity, how information is passed on, is derived. Even how boundaries are established, how variation becomes despotised, is derived. And all of these require evolutionary explanation. They don't simply transfer up from the fact that the cells have these properties. Now, how to explain the evolution of these Darwinian properties if we recognize that we need to explain them and not to take it for granted? But there are various opportunities. One is to invoke co-option, and that's definitely a possible route. So that's something I think about little raptor snowflake yeast. Many of you may be familiar with experimental evolution with yeast selecting for the types that sink to the bottom. He gets collectives of cells that on cell division remain stuck together, and miraculously, they actually give rise to offspring immediately, and that's a consequence of co-option of a gene that underpins apoptosis that was already there in the single cell form that in this new environment results in cell death and fragmentation. So there's becomes a free effect. But let's for a moment consider the possibility that these Darwinian properties don't come, that they, and this is particularly relevant when we start thinking about the origins of the first chemical replicant. There, clearly, there's nothing that's blocking. So this takes us to an interesting position. I want you to run with me for a minute, because we're not going to take anything for granted. Let me point out this first of all. If we look to multicellular organisms in the mode of reproduction, we go, that's complex. That's clearly a result of the process of evolution by natural selection. So we would want to invoke selection for the cause of reproduction. If we can't do that, of course, because that would be invoking the thing that we want to explain as the cause of its own evolution. So it doesn't reproduce, it can't participate in the process of evolution by natural selection, so you can't say selection is the cause. So if you run with this, certainly from the first emergence of life, and I think in each of the major evolutionary transitions, we begin where the entities, the initial entities, are non-Darwinian. There is no possibility of a Darwinian process or limited. And how do you get something like reproduction that is so essential to get selection working by chance alone? Maybe that's something to think about and to discuss, but that's where I am here, and I think, how do you get going? Well, this just to make this point that, again, a cell, it divides. We've got a group of cells, and that doesn't matter how goddamn big that group gets. If it never fragments, there is no evolutionary process that will take place at the level of the play. I just mentioned the word fragmentation, so of course, you could break up, and once we've got to, there's the possibility of a Darwinian process. But fragmentation, for reasons, if they're not evident, I will discuss later, is never going to get you very far. The conflicts that arise are too problematic. Heredity goes to boot. You just need to look at all multicellular organisms, and with one exception, reproduction is via a single cell. Well, that's for good reason. Because fragmentation never gets you very far. So just because the particles reproduce doesn't mean so the collective gets very far. So I want to try an idea on you that suggests that if we relax our thinking a little and integrate the interaction between organisms and the environment, it's possible to see simple scenarios that are very general, where Darwinian properties can be scaffolded, exogenously determined by the environment. Here's a simple example of scaffolding. And I'll show you a very simple model, and then I will show you, I will avoid the math, but point out that there's a mechanistic model that underpins, and I will take this further forward. But it's good just to get this intuition, first of all. So, simple example of scaffolding. We've got all that is required for the scaffolding is patchily distributed resources and the possibility of dispersal between patches. So here we have two patches. The shape will become, the reason for the shape will become apparent. Here I'm thinking about multicellular life, so I'm thinking about cells that already have a replicative capacity. There's a blue one and a red one. Blue ones grow faster than red, so I was not surprised that as time goes by, a simple time slice model here, that red goes extinct. Exponential growth ensues. Resources are now becoming depleted, hence the size of the shape of the environment. And at this stage, of course, blue is going to go extinct unless it can somehow disperse to another patch. Here, and I risk invoking multicellular life as the cause of dispersal. That could be wind, it could be a splash, it could be some physical process. Here at supply, there was a dispersal of wind that resulted in blue getting to a new patch. Okay. A bit more on the side, the shape of the patches. So red grows more slowly than blue. Exactly the same availability of resource, but because it grows more slowly, it can persist for a long period of time compared to blue that consumes its resources rapidly. So the only difference between blue and red is growth rate. There's no rate yield trade-off. That's it, growth rate, that's all. Realization of timescales working coincidentally with discretely packaged variation, particularly 2 timescales, has been, for me, a major step forward to be able to think mechanistically about evolutionary transitions. So, the timescale. First timescale is the doubling time of cells. The second timescale is the doubling time of patches here. So, if we imagine the dispersal event takes place at this point in time, then of course there are many more blue particles. The next generation of patches will soon be dominated by blue types. Let's consider, though, that dispersal takes place at this point in time. Well, now, of course, there are more red particles, and future generations of patches will be dominated by red types, even though, of course, within patches which are founded by other types, reds are outcompeted. So, nothing terribly surprising there, but it's interesting to see. If the second timescale arises late, then slow-growing types can be favored over the long. But if we continue like this, and let's draw this out a little bit further, so dispersal, we have a rare red type. So at this stage, patches are being founded just by single types because we get 2 types, the fastest growing one out this lower growing one in the patch. And another population that we think on into the future, then before too long, with a slow time scale, the slow growing type becomes. Well, patches are Darwinian. There's variation between the patches. Patches reproduce, it's dispersal, but a patch gives rise to offspring patches. And moreover, because the founding event is a single cell, the phenotype of the parent patch is evident in the offspring patches. There is the second time scale, which is all important here. And I like to think of this as if, as particle cells in this case, being unwitting players in the evolutionary process that's taking place over a time scale longer than the doubling time of the particles. And in fact, to use borrow from the theoretical frameworks, this is effectively an MLS1 way of thinking about things, but this environment, this metapopulation structure, actually distributes resources and a means of dispersal, gives us an MLS2 structure. And in fact, what I'll go and show you now is the results of mechanistic models that very simply capture the transition between single cell and something that looks an awful lot like a multicellular organism. So, I'm not going to go into the math at all. I can provide that afterward. Simply to emphasize that this is a mechanistic model built by Andrew Black, a mathematician who got intrigued with these ideas. Mechanistic in the sense that what is specified are the properties of the particles, but not the parameters, the evolutionary parameters. The dynamics that emerge at the collective level emerge from particle properties. It simply involves, it's a direct analogy with what I've just shown, particles that consume resources and divide. There is an evolutionary process that generates particles, mutation process. So particles with different growth rates, and there is also a death rate term. Here we have time along the x-axis, the number of cells. This is simply showing what's happening within a single patch at a particular point in time, actually at the beginning. colors don't show too well, but what? So here we start with a particle that has a growth rate of 1.8. You're going to see the result of implementing a long dispersal time and a short dispersal time. Mutations arise within patches, and the darker the color, the darker the color, the faster the growth rate of the mutant type is. The lighter the particle patch, lighter color, the more slow growing the particles are. And you'll see this more clearly in a moment. So this simply shows that at this particular point in time, about 16.5 units, population size is maximum. And you can see that if we have the dispersal event taking place either early or late, it's going to cause some sort of shift. So here is a movie of one of these simulations. It goes for some time. I'm going to fast forward in a moment. But we have an 8x8 grid. Cells are growing, patch size increasing and decreasing as resources are available and being depleted. The cells, at the time of dispersal, you would think of them being distributed into a global pool and then picked at that frequency and then placed at that frequency one into each different patch. If you here, for example, fast-growing cells, so at the time of dispersal, it's a very small. You can't really see it in this resolution. You can see in a moment as the colors go faster. It takes some time for the evolutionary dynamic of level of collectors to unfold here, because, of course, slow-growing mutants are usually very different. Nonetheless, you already begin to see so that patch, for example, is much larger than some of the dark blue patches. Let me just like that. It's on, and I'll show you something. You can see the color getting lighter. And so now you see primarily pale toward yellow colors, and at the time of dispersal, the number of cells is very large. Of course, selection over a long time scale is favoring those patches with slow growing cells. It's a classic within and between group selection scenario. It rises very simply, though, from patchily distributed resources and the means of dispersal. Yes, dispersal is happening at the same moment in time. No, so at that moment, right, so that's when the fly came along. So the resources are being depleted, the fly comes along now, picks up particles in proportion to the fruitfulness. That's because then we found the next group of patches from single cells. Next generation of patches. Okay. So that's what happens under a slow dispersal time, and you will have slightly surprised to see that. Now, this is kind of nice. So I like this representation. It's also the slow dispersal time. But just to show that this really is an evolutionary process that's unfolding here at the level of collector. On the simplest possible requirements. Groups becoming more fit, you'll see this here, and I'll show you the summaries. And because patches are founded by single cells, we can trace the genealogy. So here we just see a representation, I think, of these 10 patches. And if we run this through to the end, this is taken from the same simulation we just saw. You can see the circles at each time point show we've got colored early on, they're dark blue, and they're small. Because there are very few particles that survive at the time of dispersal. And at the end here, you can see the patch size has greatly increased. There's a measure of patch level of thickness. And the cells that comprising them being indicated by yellow are very slow growing. But there really is an evolutionary path of descent that can be followed. The connections work out precisely. So here we have patch evolution under the fast dispersal. Fast relative to the number of cells at that particular time point. Evolution now proceeds much more rapidly. Of course, what we're doing is favoring mutants that grow fast. So dispersal is happening during exponential phase. The faster you are, the better off, the larger your patch, the better off you are. There's nothing terribly surprising. What is interesting is the comparison that I will show you a summary of in a moment. So we get larger patches, but dominated by fast-growing organisms. In fact, you already recall the patches at the end of the slow dispersal regime were much bigger. And then if we look at the same thing here, the genealogy, once again, you can follow that genealogy. And you can see the evolution of patches happening by a selective process at the level of patches. So here's a summary of 50 simulations. What we're looking at the top here is the growth rate, data, mean cell growth rate, under the slow dispersal regime. So if the cells start growing fast, growth rate decreases, and reaches an optimum for this dispersal time. And patch size increases, and again reaches an optimum for that given particle growth rate. We see under the fast dispersal regime something quite different. Instead of growth rate of particles going down, growth rate of particles goes up. Patch fitness goes up, but not to the same extent. But here in particular, under the slow but not the fast dispersal regime, you have clear evidence of this phenomenon of decoupling, of fitness from higher and lower levels. Something that, to me, has always been rather mysterious, even though we've captured this in our experiments. But yeah, it's simply a consequence of the impact of the second time scale. It's not terribly surprising. Once that second time scale kicks in, it's happening over a doubling time that's longer than the doubling time of particles. But of course, that second time scale, where there's now a death birth event happening, holds particles directly responsible for their effects. So although selection within patches favors fast growth rate, what matters is persistence over the long time. And over the long time, patches with slow growing types will be rewarded. Second time scale long, you get this decoupling, but not when the time scale short. So, thus far, two coupled Darwinian populations from an extremely simple ecological scenario, patchily distributed resources and transmission between patches. The bottleneck is certainly a central requirement. Looked at relaxation of the bottleneck, you can relax it to 5 or so cells. It still works, but the dynamics are much slower. I'll show you some data from simply speaking about So, I guess it depends on how fast one is. And of course, if you've got a bottleneck size of 5 to 10, you may have two slow growth. It's relative. But yes, I mean, the intuition is absolutely right. You would expect. And hence, again, the reason that the bottleneck. So, probably one of the reasons that multicellular organisms produce nice so bottlenecks is precisely to avoid this conflict. Again, I've stressed this, the importance of the second time scale. One can ask, using models like this, how strict the ecological conditions are, and I want to move to a slightly more complex model, but let me just say, what rather surprised me is the extent of robustness to asynchronous dispersal. So completely synchronous dispersal and up to 8 standard deviations away at the beginning here and at the end under the slow dispersal regime. Here is a summary of the effects. So as you saw before, the growth rate of particles goes down over the slow regime. Patch fitness goes up over the slow regime, and the light green line here is 8 standard deviations from uniform in the synchronicity of dispersal time. So it's remarkably robust, actually. These set of ecological conditions, but there's much more to be done. Moving on then, so my intuition, if you've got Darwinian, let's say from a minimal set of conditions, patchily distributed resources, transmission between patches, and with the transmission event going by a single cell, we have patches that look, well, we have particles that are experiencing selective conditions as if they were members of multicellular organisms. But they are not multicellular organisms, they're patches. We take away the patches, the scaffold, it all goes. But the intuition, of course, if you've got these kin groups arising, then the possibility is set for the emergence of traits or adaptive at the group level. So we explored that by a very small addition to the model. So exactly as you saw before, that now we allow the possibility of a mutant cell type that arises, and we call these mutant types S types. So it's actually an A cell, a primary cell, that can perhaps by an epigenetic mechanism switch to produce an S cell, cell division type. Now S cells, there's the soma here, S cells are not dispersed. So they consume resources, but they're not dispersed. Not surprisingly, if we look at their dynamic on the top panel for a minute, they're not at all faded. You've seen this, this is particle cell level growth rate under the slow regime and the fast regime. This is patch thickness under the slow and fast regime. This is the rate at which these populations are producing the non-dispersing cells. It goes quickly to zero. There's no point in producing these. You consume resources, therefore patch size is reduced. The reason for having these S cells, so of course, was to now say, let's consider the possibility that S cell can contribute something to the dispersing cells. And when we do that, what we find is that S cells are favored, but only when the dispersal time is long, not when the fast dispersal rate. Now, to all intents and purposes, this has the hallmarks of a multicellular organism. It's a reproductive division of labor. Okay, it's lacking boundaries and all sorts of complexity, but out of the simplest set of ecological conditions comes something with minimal assumptions. This could be your sterile worker, for example, or your soma, and the rest is your germ life. And one point to note is that it's very clear that the S-type, soma, is an evolutionary dead end. Effectively, it's a mutation that causes the equivalent of suicidal altruism, if you want to use those words, clearly maladaptive at the level of the individual particle, but it has adaptive significance theory at the level of the group. That's why it goes. So I want briefly to move to another kind of ecological scaffold, and this is one that inspired our experiments. We've just mentioned briefly. What we have here is a pond. There are reeds in it, and around each pond is a microbial mat. They're coming in different kinds. What we need to get a Darwinian process going at the level of collectives, no intention required on the ability of the particles, the cells that make up the patches, is periodic death. And again, the means of moving, transmitting, disseminating from one patch to another. So here we have the beginnings of a Darwinian process unfolding. The properties, these Darwinian properties are purely exogenously imposed, but they can evolve to become endogenous, as we've seen. So again, we have an ecological scaffold that has variation, reproduction, and heredity simply by virtue of the nature of the environment. Now that motivated this work, which was very much ongoing, which you can see, and I'm very happy to discuss, but if I start going there, we'll never get to there. But I want to pick up one thing that came from that experiment. So here again is our pond scum. These mats are formed by microbes that overproduce adhesive polymers. It's very costly for the individuals to do them. They're selectively favored, though, because at the surface there's oxygen, there's none underneath. The microbes need oxygen. They grow slowly, but they're evolutionarily successful because of this root property. That sets the scene for the evolution of defective types, types that don't produce the glues that actually cause the mats to form. So this is a big problem, as I pointed out before. However, in this particular set of ecological conditions, what happens is that those cheating types actually become the propagules for the next generation of mats. So a problem that is there at the NRS1 level, if you like, gets turned into a solution at the NRS2 level. And in fact, we end up with this developmental program, which is rough and cranky, that selection works on it. We see in the evolution of developmental control now even environmentally responsive, switching between these phases of the life cycle. The other important thing about the life cycle is, like the dumping time of cells, which is every 45 minutes or so, this life cycle takes about 9 days. And it's prone to failure. So you get a birth-death process that unfolds for free, thanks to the emergence of this primitive life cycle. I'll finish in just a second. I think I've said enough of that. That's the idea that Darwinian properties can be exogenously determined, and they can begin to become endogenous features of the evolving system. So this idea of thinking about Darwinian processes being imposed externally actually has a variety of applications in terms of thinking about major evolutionary transitions, highly relevant to thinking about infectious disease evolution, where we are patches, for example, pathogens. And there's many parallels with models of disease evolution. Actually, a lot of interesting practical applications in terms of being able to artificially impose these Darwinian properties on collectives. It provides actually a recipe for despot, I think, to bring about an evolutionary transition in individuality, and also relevant for thinking about the origins of life. Let me just quickly, so I've been talking about a fraternal transition within, of course, the egalitarian transition, such as the evolution of the eukaryotic cell, where two different types come together. And there is some interesting thinking about humans and artificial intelligence, or just artificial intelligence per se, but just to show how this can be scaffolding works. Here is a set of cells, but it could be well, let's just keep it as cells. Yeah, we can impose these properties very simply by putting boundaries around it. It's not discrete. And we can, in the lab, very simply decide that that's not performing as we would like, but this one is a winner, so we would allow this one to reproduce and not that one. And so in the next generation, we have two offspring from that original particle. These collectives now participate in the Darwinian process. The outcome of that is the evolution of interactions, which I'll say no more about in the interest of time. That interactions between, in this case, particles become established, leading to the evolution of heritable states. There is a thought experiment that's actually now becoming a real experiment using non-fluidic devices. These are very large droplets in a tray. And we can, for example, take a red and a green bacterium, or they could be anything you like, red and green, and we can select on the color brown, for example, a property of the community. After a period of time, we can measure the state of these different communities. We can say you're too far away from the color brown, you're dead, but you guys get to reproduce. And that can be implemented in a Turing-like manner in a machine that carries out this sort of process regularly. So I'll end with this. So this idea of scaffolding, what we need for a transition to take place is Darwinian properties at the level of collectives. Well, we already exist as humans. We also interact already with fairly sophisticated artificial intelligence devices. All that one really needs here is an artificial intelligence device that one, of course, is required to have on his or her body at all time, with which one interacts, and with which through that interaction affects the fitness of the individual. And that could be anything from directing you to a particular kind of dating site to far more worrisome manipulations of individual mating behavior. Okay, so what about the offspring? Well, we don't need to embed the intelligence, the artificial intelligence devices in the germline. We just have a law that says at reproduction, your child will inherit the information from your device. Now, whether that's totally inherited or a mixture of the two, could worryingly be determined and manipulated even by a despotic regime, and the offspring receive that device. Now, for all intents and purposes, that's an evolutionary transition in individuality. You have veritable variance in fitness at the level of the two, brought about by altruism culture, and it could be enforced by a despotic regime. And it is an interesting topic, I feel, for a novel. So, to sum up, you know about evolutionary transitions, where, to me, the critical thing that needs explaining is the evolutionary emergence of these higher level Darwinian properties. It's rare, it's challenging to think about, but they can arise when scaffolded by the environment. You see that in the theoretical study, and it's also what we've done in our experimental studies. The central requirement is a specific coincidence of packages of variation with the birth-death process that takes place over a time scale longer than the doubling time. And that second time frame is kind of everything. And that it has to be longer, not shorter, is also extremely important. We saw interesting things happen when the time scale is long. There are many consequences of that longer time scale, but one of the primary ones is that selection, because what matters for persistence in the long term is survival over the long term. Selection no longer rewards over the long term fast growth of particles. In fact, it rewards slow growth of particles. Now, when that happens, cell level properties, cells themselves, are relieved of the constraint of just growing fast. So if you grow slow, it's possible to explore many new phenotypes that would come at a cost to growth rate. That becomes possible once slow growth is there. And again, in our experiments, we've witnessed quite remarkable group level adaptation, the evolution of developmental control. And I'm sure that certainly comes at a trade-off of growth rate. And it was only possible because of this second time scale. And certainly what begins as being exogenously imposed can potentially become endogenously determined. Yes, to borrow from Van Valen, I love this. Evolution is the control of development by ecology. Again, I didn't really emphasize this, but what I've done here, and particularly thanks to the work of these two, is to emphasize this ecological dimension much more than has been in the past. And Andrew Black, a Brett physicist by training in the math department of the University of Adelaide, and Pierre Bouret, a philosopher of science from France, but also in Australia, from Quarry. And they've been instrumental in thinking about this ecological scaffolding. There's a paper on the archive, and it will soon be out in the press. But with the papers there,
One quick question. You have your hand up.
The model is lovely. There are two questions from that model. One is that, of course, the dispersal time would be an evolvable trait. Then, of course, the fast replicator would, so to speak, sense it by quorum sensing that now we are dense, and then it would disperse, and then that would be quite detrimental for that particular scenario. That's point one. The second is that in the case of the multicell, the point is that the two types of cells are actually, genetically very related, right? And therefore it's epigenetically regulated. Here, the model is that they could be genetically unrelated, and it would be the same kind of thing.
The theoretical model. There, you really have to bound patches by single cells, otherwise you have a certain fundamental conflict is too large. Once you get to communities, though, I didn't mention that, but of course, so the transition to multicellularity seems to be the major challenge is to explain how reproduction works at the collective level. If it involves going to a single cell bottleneck, then to some extent the problem is heredity is solved. With egalitarian transitions, such as these communities, at least in the scaffolding way that we've been thinking about, the environment is proposing reproduction, and what has to evolve is heredity. And that emerges through the evolution of interactions between two types. In fact, we get a developmental process whereby, so after a period of time, interactions evolve, and you can have a situation where the immediate offspring doesn't look like the parent at all, but during the growth phase, it develops once again to look like the parent. So heredity becomes a thing that you can solve much of the
Thank you very much. Our next speaker, Professor Elizabeth Tibbets, the University of Michigan, and one of the major research interests is the impact of individual behavior on the social domain. Is that right? And she will talk to us today about masters.
Thank you. So thanks for trying to use them. I don't have to use the microphone, right?
Yeah.
No, just.
All right, well, thanks so much. All right, well, thanks so much for inviting me. This looks like we're going to have a lot of interesting discussions. So I study paper wasps, and one of the reasons I think paper wasps are cool is they're kind of at that transition between individuality and cooperation. And so they're kind of different than other social insects that you typically think of. So if you look around the room, you'll notice that there is an enormous amount of variation in human faces. So everyone's face pretty much looks different. And the fact that we're all so unique is essential for our social communication system to function effectively. Just imagine what life would be like if everybody looked the same. It would be a crisis, right? How would you differentiate between your friends and your family members and your colleagues? You wouldn't be able to tell anyone apart if we all looked identical. So variation within the group is essential for communication. So with that in mind, today I'm going to talk to you. Am I doing something wrong, or is it just?
No, it's okay.
It is working.
Try now.
Just very slowly.
Time up. Okay.
Let's see.
Let me do it. See if I'm doing it wrong.
Is this one?
Okay, stay over here. So just click it. Just click it. Here we go. Okay, so I'm going to talk about Felicity's paper wasps, and you'll notice that they have a huge amount of variation in their facial features. I'm going to talk about how they use the variation and how this influences their cognition and their cooperation. Okay. Soon I will get the hang of the AZ. Okay, so I'm going to start by telling you what their social behavior is like. So in the spring, they come out of diapause and they start a nest. They can either start a nest alone or they can start a nest with a group of other queens. And when they start a nest in a group, they form a linear dominance hierarchy where the dominant wasp gets all the reproduction and the subordinate wasps do all the work. So it's kind of an interesting question. Why do they form these cooperative societies? Yeah, the subordinates get kind of a raw deal. So when I first started grad school, this is what I was interested in studying. And this shows you, this video is each of these little dots is a wasp. And each of those numbers is a different location. And you can see when they first start nests, there's a lot of exciting transitions between cooperation. So there's some individuals that form fairly stable associations. There are other individuals that are moving all around trying to find the right individual to nest with. So there's a huge amount of dynamism here in their cooperative behavior. And they spend a lot of time figuring out who should I cooperate? I don't know. They don't seem like such a good social partner after all. Do I want to form a cooperative group, or instead do I want to be independent? So you can see there's a lot of flexibility in the kind of social decisions they make. Okay, so this is what their life cycle is like. They come out of hibernation in the spring, they fight with each other, they check out a lot of different nesting sites. Eventually they settle down, start a nest, either alone or in a group. And then we have the workers who are cooperative and help rear future generations of reproductive females and males. So kind of an interesting thing about paper wasps is that this worker phase is not something that the wasps are stuck with. So you usually think of workers like in honeybees. The workers are pretty much not reproductive. They can occasionally produce males, but they don't have many independent reproductive options. And instead, you can think of them as, maybe some people think of them as cells in the body of the colony. But it's different in paper wasps. So these workers do have the option of reproducing on their own. They look just the same as queens. They can go off and they can enter hibernation in the middle of the summer and start their own nest. So you can see these guys are incredibly flexible in their options of whether to cooperate or not cooperate. So when I first started studying them, I was interested in understanding why they cooperate. And so the first experiment I did involved marking wasps with little dots on their back and then videotaping their behavior. And unfortunately, one day I ended up with 2 unmarked wasps on the nest. And I thought, oh, maybe I'll just watch the video anyway and see what happens. This is not that video. It's another video of 2 unmarked wasps walking around. Can you make it? Can you make it quick? Interacting, doing little wasp things. And as I was watching this video, I noticed that the wasps look a little different. Maybe they don't look different to you, but they look a little bit different to me. I've shown this video to other people who think I'm crazy. They say they don't actually look different, but they do. So I noticed this and I went out and I collected wasps from a bunch of colonies. And I noticed that there was a huge amount of variation in their color pattern. So you can see there's variation in this little part in their inner eye, in their clypeus, up there in their eyebrow area, and also in their abdomen. So these are all wasps collected from a very small area. They're all of the same species, but they look different. We did some experiments to show that these wasps have individual face recognition. So they learn each other's unique faces when they meet. And then next time they meet, they don't need to fight again. They can just say, oh yeah, you're Susie. I remember we fought last week and you were really strong. So individual recognition is kind of a complicated social behavior, and it opens up the doors to many more sophisticated social behaviors. If you know who's who, you can do a lot more interesting social things than if you don't know who's who, right? So individual recognition is interesting, but there's kind of a wide swath in the complexity of individual recognition that you can find. So humans, we have incredibly sophisticated individual recognition. We learn lots of individuals. We know a lot about them. We know a huge amount of information about our past history of social interactions. And we can maintain those memories for long periods of time. Wasps, obviously, it's a little simpler, but we spend a lot of time thinking about how complex is their recognition? How many individuals can they learn? And how does it influence their social behavior? So the first thing we found is that they can use individual recognition to learn and remember each one of their nestmates. So their colonies are not that big, maybe 15 wasps on a colony, and they know everyone on the colony and their individual identity. We also know that they use individual recognition during their interactions with competitors off the nest. So if 2 wasps fight, they'll remember the unique identity of the winner, and then they don't fight that individual again. Similarly, they'll remember if another individual lost to them, and then they will dominate them immediately. Okay, so that's pretty cool. They have some complexity of their individual recognition. But recently I started wondering whether wasps could learn about other individuals by observing contests. So in the spring, like I said, you got some wasps fighting, you got a lot of wasps flying around, and it kind of looks like they're watching the fights. So I wanted to know whether they could learn about each other just by observing the contests. So lots of animals learn about each other by observing contests. It's obviously super important to humans. You watch 2 people interact and you learn a lot about what's about to beat those interacting partners without needing to engage with them. Same thing happens in a range of primates. You can see them found in fish, that fish watch each other fight and learn from that observation. So I thought, hey, wasps are really smart. Let's see if they can do the same thing. So to do this experiment, these are 2 fantastic undergraduates who actually ran this experiment and watched all the videos. The way we set it up is we had 2 wasps fight, and then we had 2 wasps watching the fight. So these watchers couldn't interact. There was glass between them. They couldn't smell each other. All they could do was see the fighters. This is a video of this going on. You can see the fighters over here. Oh, sorry. This wasp is really watching what's going on. This wasp is completely uninterested in what was going on. There's variation in how interested they are. Okay, so that was the initial setup. We had these watchers observing the fights. And then the next thing we had to do was set them up in different places. So, what we did is we took a fighter and we paired her with an observer who'd seen her fight. And we expected if she learned something by watching that fight, that observer would act different than an observer who had not observed the fight. And then we had some fighters over here who were paired with observers who'd seen a different fight. So this observer here saw a fight, but she did not see that particular individual fight. So she couldn't gain information about that individual by watching the fight. Okay, so we had wasps fight, we had wasps watch fights, and then we set them up in even more things. So there's three interesting things that could go on here. The first one is the one that I think would be the most interesting. So the observer behavior could be influenced by seeing their rival's previous fighting behavior. So she could say, wow, I saw you, Susie, and you were so tough, you beat up on everyone else. Even though I've never interacted with you before, I am just going to immediately submit to you because I saw that you're super tough. The second possibility is observer behavior could be influenced just by seeing aggression. So a wasp sees a lot of aggression and she thinks, oh, aggression, that's exciting, I'm going to be aggressive too. Or she sees a lot of aggression and she thinks, oh, I don't feel like fighting, I'm just going to stop fighting. That's less interesting because it doesn't involve remembering individuals, but it's possible. And the third possibility is that fighter behavior can be influenced by her previous fight. So maybe this individual, she wins a fight, so she's really feeling really good about herself, so she wins all future fights, and it has nothing to do with this observer. Okay, so we tested these alternatives. First of all, we saw that observing aggression of a different rival doesn't influence behavior. So this is the aggression initiated by the fighter, and then this is the aggression that was the observer initiated when they next interacted. What you can see, I'm sure, is that there's nothing there. There's absolutely no relationship. And what this tells you is just seeing aggression doesn't matter. So if you see random wasps fight, it doesn't change a wasp's future interaction. So this graph also shows no relationship. What you can see is that aggression influence is not influenced by the previous fight of a rival. So that's kind of like winner loser effects. Often in animals, if you win a fight, you become more likely to win future fights. And this shows that that isn't going on here at all. Whether a fighter is aggressive or not aggressive, it doesn't influence their future fighting behavior. But what we did find is that wasps establish dominance with less aggression if they observe their rival being aggressive. So this is the aggression initiated by the fighter in a previous context, and this is the aggression initiated by the observer. And what it shows you, if a wasp sees their rival fight a lot and be really aggressive, they basically give up immediately and they don't even bother trying to fight. So that tells you that they're keeping track of individuals, they're watching them, they see Susie be really aggressive, and they say, okay, I am not going to mess with Susie, I'm just going to give up. It's not. So there was another important factor in this model, perhaps not surprisingly, the amount of time they actually spend fighting, observing matters. So when some of the time they actually watched their rivals fight, and some of the time they were distracted and looking for a way to escape. And you can see if they looked more, if they watched these aggressive interactions, then they gained more useful information, which is again not surprising. So overall, it turns out that wasps do actually keep track of these social relationships. And I'm going to say that the R squared on that model was 0.71. I think that is the highest R squared of my life, and I actually can't believe it. So it tells you that observing contests has a really strong impact on wasp behavior. Okay, so they learn about the rivals via observation alone. And I have to admit, when we first did this project, I did not expect it to work. I thought there's no way that wasps are smart enough to do that. So I guess that shows you that you shouldn't underestimate your study organism. Their brain is like the size of a grain of rice, but they're still pretty complicated. And I think this potential that tells you that their social life is more complicated than I originally thought. They're living in a complex world where they know lots of individuals and know a lot about each other, which could have interesting implications for their evolution of cooperation. Okay, so finding this result, it made me wonder whether wasps are capable of something called transitive inference. So transitive inference is using what you know to make inferences about what you don't know. So in this case, if I tell you that John is stronger than Sally and Sally is stronger than Pete, it's known information, I can ask you to make an inference. So do you guys think John is stronger or weaker than Pete? What do you think? Congratulations, you guys can do transitive inference. Amazing. John is probably stronger than Pete. So long ago, people thought that transitive inference was kind of the hallmark of human cognition. We thought that only humans could do it, and it was based on logical inference. Now, with everything that we think is uniquely human, of course, it turns out to not be unique. And transitive inference has been found in many organisms. It's very common in primates. It's also found in birds, and even in some fish. There's been one study on transitive inference in an invertebrate, and that was done in honeybees. And they found that honeybees failed the transitive inference test. And which is kind of surprising because you know that honeybees can do a whole bunch of complicated things. So I, of course, think that wasps are much smarter and more talented than bees. So I wanted to test whether wasps could pass transitive inference. Okay, so the way you test transitive inference is you first train individuals on a bunch of different relationships. So that's the known information. And then you ask them to make an inference about an unknown relationship. So basically what we would do for wasps is we'd say, okay, let's say blue is safe and yellow is associated with electric shock. So that means blue is better than yellow. And then after they got that, you tell them, okay, yellow is safe and green is associated with electric shock. And then you say, okay, now we've got that, green is safe and purple is associated with electric shock. And then after they got that, last of all, you would say purple is safe and light blue is associated with electric shock. The order, yeah, so that's a good question. Order could matter. So you train them both this way, starting with A and B first, and then you also have to train them this way, starting with D and E first. Be sure to order them. So you switch up the order. And then also you switch up the colors. Obviously, that's important, so they're not making decisions because they really like one color. Okay, so now they have all of this information, and then you ask them about this pair. They say, hey, B versus D, which one do you like better? The idea is if they have transitive inference, they will choose B over D, and if they don't have transitive inference, they will choose random. So in order to show transitive inference, you need to show these three things. First of all, they need to learn all four of these pairs. And this is actually where B's fell down. They couldn't do it. After you told them that A is better than B, then you tried to train them that B is better than C, and they were like, what? You just told me that B is bad, and now that it's good? That's so confusing. I can't change my mind. So first of all, they need to learn all the four premise pairs. They need to remember them for the whole experiment. It takes a couple days to train them. And then they have to choose B over D when given a choice. And this is the way that we train wasps. This was an experiment done by another three fantastic undergraduates. So we train them in these little rectangles where one part has an electric shock and one part has a safe zone. And then in this case, they would learn to go to the purple to avoid being shocked. Now, when we actually test them, there's no electric shock so that they aren't making decisions based on the shock. They've already learned. All right, so our first test, do they learn to discriminate all four pairs of colors? And the answer is yes, they do. So this is the number of correct choices out of 10. The dotted line is the 50-50 random expectation, and you can see they choose better than random chance. So they've already beaten honeybees. Yay, congratulations, wasps. They learned those four pairs. So the second part is we need to remember them for the whole experiment. So to test this, we retested wasps on day 4. That was at the end, the very end of the training. And they did just as well on the retest than they did the first time we trained them. So they remember. Good. And then last but not least, they need to choose B over D. And you can probably guess, because I'm telling you about this experiment, that they did in fact choose B over D. Again, the dotted line is a 50-50 random expectation. They chose B significantly more often than you would expect. Now, like I said, there was no shock in the arena. We even had the trainers do this blind, so they didn't know which one was B and which was D, so they couldn't accidentally confuse the wasps. So this tells you that the wasps take all those pairs of stimuli that we trained them to, and they organize them in a linear hierarchy in their brain, and then they use transitive inference to choose among those stimuli. Now, it's tempting to say that the reason this happens is because wasps are much better than bees. But I'm not actually going to say that, even though they are better. I think the reason that there's this difference in their social behavior, in their learning ability, is because of differences in their social behavior. So bees, they live in a world where there's a queen, there's a bunch of workers, the workers are all equally ranked. Wasps, on the other hand, have linear dominance hierarchies. With the queens, with the workers, everyone lives in a place in the hierarchy. The transitive inference is really helpful if you live in a hierarchical world, because it helps you make inferences about who you're likely to win beat and who you're likely to lose to without engaging in a fight. So I think it's the social behavior of an animal and the life they live and what they need in order to be successful that influences their cognitive abilities. So even if you have a tiny little brain the size of a grain of rice, you can do transitive inference if you live in a world where managing social relationships is important. Okay, so many of you have probably heard of the social intelligence hypothesis. The idea is that animals with complicated social interactions and individually differentiated social relationships are smarter than other animals. That's one of the hypotheses for why humans are so smart. We keep track of so many individuals in our relationships with them. So of course, humans, we're smart. Many birds with these complicated social relationships are smart. And the question I have, is, do wasps belong here or not, right? They have individually differentiated social relationships, they're cooperative. How smart are they really? And in particular, we can do a little bit more refined test. Obviously, wasps are probably going to be the dumbest ones up here. But compared to other species of wasps, are species of individual recognition smarter than the species of that. So this is Polistes gustatus. You can see they have different faces, individual recognition. Over here we have Polistes metricus. So they're a close relative in the same genus, but they don't have individual face recognition. And we think the reason they don't have individual recognition is because they have a very simple social life. So usually nests are started by only one queen. You don't need individual recognition to keep track of that. So we were interested in testing whether Polistes gustatus is smarter or not than species without individual recognition. And this kind of gets at a more general question about how animal minds evolve. So does our capacity for doing complicated things evolve in a specialized or a generalized way? So most of what we do involves very widespread processes that are used in many animals and in many different contexts. And that makes sense because you can't be specialized for every single thing you do. It's just not possible for you to be specialized for each task that you do. But there are some examples of specialization that have attracted a lot of attention, and people have wondered why and when this specialization happens. So one of the best studied examples of specialization is face recognition. So primates with individual face recognition are specialized for learning faces. Humans, we are amazing at face learning. You probably don't even think about it, how incredible we are, but we really are good. I mean, you know the faces of everyone in this room already, even if you haven't consciously spent much time thinking about it. So I'm going to test your face recognition. Which one did I show you? Yeah. I showed you him. If you were paying attention, I only showed it to you for a second, and you got it instantly. Can you imagine any other kind of pattern I could do that with? No. There's no way you could do that with anything. So humans are specialized actually for right side up. What? I should. That's what I don't know why. So we're so specialized for faces that if you change a face a little by turning it upside down, it becomes much harder. So chances are you can still find the face, but it's more difficult because our brains don't interpret upside down faces as faces, which is amazing because they're composed of the same colors and patterns. I mean, the faces are identical, but your brain no longer identifies it as different faces. So here's an even more striking example of that. So those faces, they probably look similar to you, maybe. They're not similar at all, right? But your brain totally missed that because the special part of your brain, the fusiform face area that's primarily for faces, doesn't identify upside down faces as faces. And so you process upside down faces using your general pattern recognition, which is way worse than your face recognition Okay, so we wanted to know whether wasps are also specialized for learning other wasp faces. And this is a project that was done by my old grad student, Mike Sheehan. This is one of the many undergrads who spent a lot of time training wasps. So we said that if these wasps are specialized for face learning, they'll learn faces better than they learn other information. So we tested their ability to learn faces. We also tested their ability to learn non-face patterns. So we tested them on black and white patterns that honeybees are really good at learning. And we also tested them on caterpillars because wasps eat caterpillars. And then we also tested their ability to learn manipulated faces. So manipulated faces are composed of the same colors and patterns as regular faces, but we've mixed them up a little bit so that their brain can't identify them as a face. So in some cases, we jumbled up the parts of the face. And then in another case, we just digitally removed the antenna from an image. So the antenna don't actually have any variation on them, so they're not really important for individual recognition, but it turns out they're an important cue that it's a face for a wasp. So then we tested their learning ability, and what we found is, yes, in fact, the wasps are much better at learning faces than they are at learning non-face patterns. So this is the percent correct out of 10. You can see they excel at faces. So even more surprisingly, they are much better at regular faces than manipulated faces. And I was particularly struck by the fact that just digitally removing the antenna from the image dramatically reduces their face recognition ability. So we've done future studies showing that they use holistic face processing, and this is removing the antenna just eliminates their ability to do this holistic processing. So this is really strong evidence for specialization that their brain is attuned to faces alone, and if you do anything to mess it up, they become much worse at face recognition. Okay, so one of the nice things about studying a paper wasp is that there are lots of close relatives. And you can see that this species here, I already mentioned, lacks face recognition. So we wanted to test whether they also lack face specialization. And we decided that if individual recognition is the key selective pressure that has led to face specialization, then a species like this that lacks individual recognition is not going to be good at face learning, and they're not going to have face specialization. So we took the species here, Felistes metricus, we trained them to faces, and they couldn't learn them at all. They did much worse on face learning than they did in pattern learning. Now, there is a little bit of a problem with this. There's a little bit of a problem with this study because this species doesn't have much natural face variation. So we had to add variation using Photoshop, but maybe we added it poorly, and that's the reason that they can't learn faces. These faces. So what we did is we tested both species on each other's stimuli. So this is the results of the species with individual face recognition. You can see they learn their own faces very well, and they even learn the other species' faces better than the other species does. So these guys are just expert face learners no matter what kind of face you give, wasp face you give them. This is a species without natural face recognition. And the interesting and surprising thing here is that they learn the other species' face is better than their own faces. So that actually kind of makes sense if you think about it. It suggests that the faces of Felistes cristatus have been selected to be really easy to learn and remember. So there's been selection on the senders to be individually recognizable, which is actually similar to what happens in humans. There's some interesting studies showing that human faces have been selected to be highly variable. They're more variable than other areas of the genome, suggesting their selection on us to look distinct so we can tell each other. Okay, so even though there's this difference in face ability, there's no difference in general learning ability. So the species with individual face recognition and the species without learn colors and patterns similarly. So it's not like individual recognition just makes these wasps smart at everything. They're only smart at the very specific thing they need to do to be successful, which is learn and remember other individuals. So the challenge of individual recognition has shaped cognitive evolution of paper wasps, but largely via specialization. All right, thank you so much for your attention.
first part, when you see two others fight, it makes you want to give up more in your next fight. Doesn't that destroy the bit for trading dominance? Like if the dominant one is seeing two subordinates fight, become less dominant? Isn't this stabilizing?
I think it's not just saying any wasp fight, that if the wasp is very aggressive, then it makes you want to give up. But if you see a wasp who's not very aggressive, then it doesn't make you want to give up. Does that make sense?
Don't they need some kind of experience? How much context, right? But they've never fought.
Yeah.
How do they know where they're going to rank?
Well, that's it. They just like, it's not worth it.
Oh,
I'm just
so
going to
what's
give
the
up now.
benefit to fighting? Why do they fight?
So I should say that they fight over many things. One of the things they fight over is dominance, rank, and a nest, which is incredibly important and determines their entire lifetime reproductive success. So what we would expect to see, although I didn't test it, is how much they rely on social information should vary based on context. So if you're fighting over something really important, it's life or death, if you win it, you're going to have high reproduction for the rest of your life, you probably shouldn't rely on social information, right? But on the other hand, many of these fights, they're just kind of feeling things out. They're not quite settled down. And in those situations, maybe the cost of fighting is high enough that it makes more sense to pay attention to social information.
Have you ever done an experiment building to wasps that have never fought? And how do they behave differently? So
Yeah,
wasps that have experience.
Yeah, all these wasps in that experiment were wasps who've never met before. They've never seen each other before.
But you've never fought with any other wasp.
Oh.
That's what I wanted to know.
Okay.
Just how do you know when you've never, maybe the best answer is let's know.
So that was an interesting experiment. I have to think of a way of getting at it well. But if you take a wasp who's never experienced other wasps, socially rejected, it will not, it can't even recognize other individuals. So they need experience to get good at these sorts of things. So they need a lot of experience actually to get good at it. Yeah. Totally. So that's another experiment to actually see how transitivity works within their nest. And that's totally an experiment we should do. I just haven't done it yet, so it requires a lot of wasp fights and it takes a long time. Yeah, so the transitivity was in a kind of an arbitrary situation, not yeah, next question.
I'm sure that's a lot of stuff having to do with the relationship between recognition of individuals and fights, struggles over dominance. So, in humans and other species, the recognition of other individuals is also very important for cooperation. Who do I cooperate with? And you haven't said anything about that. So, is there significance for face recognition in terms of cooperation between different individuals?
Yeah, that's so interesting, and nobody has studied that at all, but I think it could be really important because in addition to watching each other fight, they watch each other being cooperative. So there's variation in how cooperative they are. Some wasps are really helpful, other wasps are not as helpful.
Can you say a few more sentences about what it means to be more or less helpful?
Yeah, so in wasps, being helpful means like you share your food with other wasps. You come back with food, and instead of taking it all, you share it. It means doing more work instead of just like sitting around on the nest eating all the time.
This is stuff you can follow.
Yeah,
so
yeah.
Basically, you can put these wasps in those cells and let them see more or less cooperative individuals, and then see whether they choose.
Theoretically, you could. Yeah, this is very interesting.
In the context of the superorganism, the transition is this feature important? Because bees is a superorganism and is intelligent at the collective level. So, what is the importance of this? Will humans lose the ability of recognition toward a superorganism, or?
Yeah, I mean, individual recognition is the cornerstone of human society for sure. I think that individuality is important for, I would say, social species that have not yet made the transition to superorganism. And I think that is where it is most common. It's incredibly widespread in that situation. But species that are superorganisms don't have it.
They're more homogeneous.
Yeah, they're more homogeneous.
Are they always kid groups?
Yeah, No, they're not. So you would think they would be. They're often in, but they often cooperate also with unrelated individuals, which makes the question of how they choose more.
So, individuality could also be helpful when you want to put some sanctions on individuals when they violate some community norms. So in that sense, it could also help with the transition. When you have that, it could allow you to put those sanctions on individuals.
For sure. And there's some evidence that happens in mosques, not mine, but punishment for individuals who are not cooperative.
Yes, it would help this community.
Exactly.
So when you said you said that thing, they're still in the process, though they haven't made the transition yet.
Yeah, they're not going to.
They're not going to. You're saying they're not going to. So they're not in the middle of a process. They are somewhere that is no longer something that is totally individualistic, because there is some cooperation, but that's where they are. Can you characterize this place where they are? So, for example, in terms of communication, in terms of information sharing, how much is there? Food sites, dangers, and so on.
I would say that's a question that we're still trying to answer. And a lot of things like social learning, which are really important, highly social species, I think they also happen in wasps, but nobody has studied it yet. Yeah. But that's a very good point. Thank you. They're not making the transition to sociology. They've been in this place where they are for a long time, and they're not taking it.
It's a mind bugger for me to see that the bee colony is much smarter in a way than the wasp colony, whereas the wasp is probably much smarter than the bee. Do we want to go there?
Yeah, I think we'd be horrified at what would happen. Yeah, but it's in a transition. It would be that difficult. It is the way.
This is also what is said for some of the other social traumas. Individually, we are not necessarily smarter than they are, but we have become much smarter because of our culture. Put a single individual and a single private, we are not necessarily smart.
Yes, and there is evidence for that in the entire experiment. So now we have a full hour for our next coffee break, because as I said, we have another task. We need